the Nuclear Engineering Department head here at the University of Tennessee, and welcome to our Nuclear Engineering Graduate Colloquium program. Today we're fortunate to have Dr. Karen Miller as our speaker. She's a nuclear non-proliferation expert at Los Alamos National Laboratory. She recently completed a 2-year assignment at the U.S. Department of State. Prior to that, Dr. Miller spent over a decade with the Safeguards Group at Los Alamos. She is also the U.S. member of the IAEA Director General Standing Advisory Group on Safeguards Implementations. She has a bachelor's and a PhD in nuclear engineering from Texas A&M University. Go Aggies!
All right, good afternoon, everyone. Apologies for the technical difficulties. I am going to turn my video off just to save my bandwidth. Thank you all for joining. I am coming to you from Washington, D.C. I wish we could be doing this in person, but hopefully sometime soon. So when Professor Hines first asked me to give this talk, I thought a lot about what I might have wanted to hear when I was a nuclear engineering graduate student. Specifically, what kind of jobs are out there for me. So the talk I pulled together is meant to give you a snapshot of one possible career path in nuclear engineering, specifically supporting the global nuclear non-proliferation regime. And hopefully give you a sense of the kind of opportunities you might have in the field as a nuclear engineer. Next slide. All right, again, to give you a little bit more background about me, as Professor Hines says, I have a bachelor's and PhD in nuclear engineering from Texas A&M. I began working at Los Alamos National Lab in 2003 when I was still a student. So I was in college when 9/11 happened, and like many other people, those events motivated me to go into the national security field. So I have spent the bulk of my career so far working in non-proliferation and safeguards. At Los Alamos, I have had experience as both a scientist and a program manager. In my primary area of technical expertise is in non-destructive assay systems, or NDA systems, for uranium and plutonium measurements. So in other words, I'm an expert on radiation detection and measurement. And also, just last week, I finished a 2-year assignment with the State Department working on foreign policy and diplomacy as it relates to the nuclear non-proliferation regime. Okay, next slide. So for my talk, I'm going to begin with a very high-level introduction to IAEA Safeguards to make sure we're all on the same page in terms of topic area. Then I'm going to talk about how Los Alamos supports a strengthened safeguards regime. I'll give you a sort of big picture overview of the lab's work, and then talk about a few specific examples. And then I'll wrap up with a few concluding thoughts. Next slide. All right, so for context, the Nuclear Non-Proliferation Treaty, or the NPT, is the cornerstone of the global non-proliferation regime. Article 3 of the NPT requires that all non-nuclear weapon states party to the treaty accept safeguards negotiated through an agreement with the IAEA. So the IAEA is an international organization based in Vienna, Austria, and the Safeguards Department at the IAEA monitors nuclear material and facilities around the world to provide credible assurances that nuclear technology is used for peaceful purposes only. So the IAEA has no dedicated budget for research and development. It doesn't have any specialized facilities for training its staff or testing equipment. So IAEA member states provide support to the IAEA to help ensure it's able to deploy the state-of-the-art tools and techniques and methodologies to carry out its safeguards mandate. So hopefully, this is a very high-level view, but hopefully I've laid out for you, why Los Alamos and many of the other national labs are involved in this work. So for the rest of the talk, I'm going to discuss, how the labs do that. Okay, next slide. So Los Alamos has a dedicated safeguards group. The work that the group does covers the full life cycle development of safeguards instruments and methods. So this is everything from basic and applied R&D to technology deployment in the field to training the people who might use these technologies. So just a note about the training mission and this screenshot on the right side of the slide. So Los Alamos is very proud to have trained every IAEA inspector since 1980. Several years ago, NPR came to the lab and did a story, about the training courses that the lab puts on for IAEA inspectors. So you can actually look this up if you're interested. I think it's, kind of a cool little story. So the staff in the safeguards group at Los Alamos have an enormous amount of experience in nuclear material processing. So this work is highly multidisciplinary, meaning you get to work with a diverse set of experts. So in addition to nuclear engineers and physicists, the group has resident or pools in experts from around the lab in areas like mechanical engineering or electrical engineering. There's chemists, there's machinists, we rely heavily on computer scientists and mathematicians. So, you get to work with, just a really diverse set of experts. So another great part of working with this group is that you have access to the nuclear facilities and the nuclear materials at the laboratory. So the lab likes to say it takes a nuclear weapons lab to find a nuclear weapons lab. And last, here, just a plug for any of you who are interested in this kind of thing. This kind of work also gives you many opportunities to go live abroad in Vienna and work for the IAEA for a few years, if you're interested. Next slide. Okay, so now that I've given you sort of a high-level overview of the lab's work in safeguards, I'm going to talk about a few specific examples, starting first with an applied research example. Here I'm going to talk about some of the work I did over a number of years looking at UF6 cylinder measurements for enrichment plant safeguards. Next slide. All right, so to start, the basics, uranium at gas centrifuge enrichment plants is processed in the form of uranium hexafluoride, or UF6. UF6 is stored in cylinders when it's not in process. And there are a number of standard UF6 cylinder types that range in size, everything from a 1.5 inch diameter cylinders to very large cylinders that are 48 inch diameter. So this portfolio of projects was aimed at advancing NDA techniques for verifying UF6 cylinders, which is a key component of enrichment plant safeguards. So, the amount of UF6 that's actually in process at an enrichment plant at any given time is typically much smaller than the amount of UF6 that's actually in storage cylinders. So the work I'll describe here is work I did over 2010 to 2016. It was funded by both the NNSA Office of Nonproliferation Arms Control International Nuclear Safeguards Program, or NA-241, as well as the Office of Nuclear Verification, or NA-243. And just to give you a sense of the scale of that work, over that time, I measured over 400 UF6 cylinders on 3 different continents. Next slide. All right, so the first system, excuse me, the first system I'll mention is one called the Passive Neutron Enrichment Meter, or PNEM. So PNEM is a helium-3 based neutron coincidence counter. And actually, I'll say all of the systems I'm going to talk about here are helium-3 based systems. PNEM is designed to measure both the U-235 mass and enrichment of the uranium in the cylinders. I find generally there are many more people who are experts on gamma ray measurements than neutron measurements. So, so I'll say, you know, gamma ray measurements, gamma ray spectroscopy, you're typically looking at, you know, the energy distribution of gamma ray interactions in a detector. So sort of analogous to that, in neutron coincidence and multiplicity counting, you're typically looking at the time distribution of neutron interactions in the detector. So I'll talk about here the difference between sort of random neutrons from alpha N reactions versus correlated neutrons from fission. Those are the kind of, that's the kind of information that helps you understand the characteristics of the material in sort of neutron coincidence counting. So for the U-235 mass measurement, we looked at random alpha N neutrons from U-234 alpha bombardment of the fluorine in UF6. So, you know, heavy isotopes like U-234 decay by alpha emission. Those, you know, alpha particles interact with the light elements like fluorine and give you neutrons that are random in time. So, you know, the next, you know, obvious question is, okay, how do you translate U-234 into what you're really after, which is U-235 mass? So when you enrich uranium in a centrifuge, you are enriching the, you know, light isotopes of that material. So you're pulling out, you know, you really want, you know, to enrich U-235, but as you're enriching U-235, you're also enriching U-234. So the enrichment of U-234 tracks the enrichment of U-235 in very predictable ways. So this technique relies on a known U-234 to U-235 ratio, which for, you know, most safeguards use cases is a safe assumption. So for the enrichment measurement, you're looking at correlated neutrons from self-induced fission in U-235. So for those of you who study radiation detection, you may know that gamma rays are subject to self-shielding, meaning they don't travel that far in uranium. Neutrons are much more highly penetrating. So one of the main advantages of these neutron methods, especially for assaying large items, is that you get a much more full volume assay with a neutron technique. So just to drive this point home, this photo I have on the right is a picture of me and one of my colleagues from Los Alamos standing next to the largest of those standard cylinder types I mentioned. This one's called a 48Y cylinder. And these are typically used to hold natural and depleted UF6. Okay, next slide. All right, so the next system I'll mention is one called the Unattended Cylinder Verification System, or station, or UCVS. So this was an extension of the work I did on PNEM. I was involved in the first phase of this project, which was a viability study for an unattended monitoring system for UF6 cylinder verification. So when I say unattended monitoring system, What this means is that it does not require the physical presence of an inspector. So the idea is that the IAEA could potentially assay all of these cylinders at an enrichment plant as opposed to just measuring some random selection during on-site inspections. So PNEM was one of 2 NDA systems in the phase 1 prototype. The other one was a system developed by my colleagues at Pacific Northwest National Lab, PNNL. It's called the Hybrid Enrichment Verification Array, or HEVA. This was also a multi-lab effort, including experts from, obviously, from Los Alamos and PNNL, but also Oak Ridge and Savannah River National Labs. So I'll just mention here as an aside that one of the great things about working at the national labs is that you not only get to work with world-class experts in all kinds of scientific disciplines at your own lab, but often you also get to work with experts from all over the DOE complex, which for me it has been really fulfilling and really great. For the UCVS study, we did a field trial at the Westinghouse Fuel Fabrication Facility in South Carolina. They were very generous and let us test our systems over an 8-month duration. One of the key outcomes was a quantitative evaluation of both the 2 NDA systems being considered for inclusion in a UCVS. We published a number of articles on this work, but I put this reference here to an article that we wrote for Nuclear Instruments and Methods, if you're interested in learning more about that project. Next slide. Okay, so next up is small cylinder measurements. Here you can see 2 systems I worked on for measuring 1.5 and 5-inch diameter cylinders. These systems both have options for either passive or active neutron measurements. So in the case of an active measurement, where the system would include an external neutron source for inducing fission in U-235, you actually get a direct measure of U-235 mass, as opposed to passive mode, where again, you're really measuring U-234 mass and converting it to U-235 mass based on a known U-234 to U-235 ratio. The system on the left is one called the Mini Epithermal Neutron Multiplicity Counter, the Mini ENMC. This is a very high efficiency system. So it has just over 110 atmosphere helium-3 tubes. They're in 4 concentric rings. So it can be used to measure the smallest of the UF6 cylinders. You can see that's me holding on the left one of those cylinders. If there was a need for this, the system can actually come apart. It splits in half, so you could, in theory, also use it to assay a larger cylinder. Okay, the system on the right is one called the UF6 Coincidence Counter, or UFCC. So it's used to measure 5-inch diameter cylinders. These cylinders hold up to 25 kilograms of UF6. They are commonly used to store near 20% enriched UF6 for research reactor fuel. Okay, next slide. Okay, so I suspect that many of you are either developers or users of the various modeling and simulation tools that fall within sort of the nuclear engineering toolbox. These are codes like MCMP or Scale or others. So I wanted to mention here that from the practitioner level, these modeling and simulation tools are integral to the kind of work that I have been describing. So very often we start by, so I used MCMP as my sort of primary modeling code. So very often I would start by building a model of my detector in MCMP, and then carefully validating those models against measurements with characterized calibration sources. This picture and plot sort of on the top right shows maybe a little bit how we do that. Modeling studies can give new insights into physical phenomena. The tools allow us to explore scenarios where experiments are cost prohibitive. And we also use them for things like sensitivity analysis and uncertainty quantification. All right, next slide. Okay, so for my last slide on UF6 cylinder measurements, I thought I would just mention here the importance of good nuclear data. So when I first started working on UF6 cylinder measurements, one of the things I did was go to the literature and try to find, publish data on things like what are the number of neutrons emitted per second per gram of U-234, so I could feed those numbers into my simulations. And what I found was that there was a big spread in what those published values were. I was trying to remember off the top of my head. I think it was, something like 20% difference between the max and min values I found in the literature. So over time, I was able to perform some analysis that combine high fidelity measurements of well-characterized UF6 cylinders with those very carefully validated MCMP models and detailed uncertainty quantification and sensitivity analysis to publish my own values. But I will say, that was a limited study, limited scope study, and in my opinion, this is an area that is still ripe for more work. All right, next slide. Okay, so the next example I wanted to talk about is more on the basic research side of the R&D spectrum. So this is a little bit more like big data meets safeguards. All right, next slide. Okay, so this work was aimed at exploring whether characterizing activity patterns across disparate data streams could provide the IAEA with enhanced capability to detect misuse of or diversion of nuclear material from safeguarded facilities. We used machine learning methods to integrate persistent and heterogeneous data streams in order to identify those activity patterns. This work built on the idea that the whole is greater than the sum of its parts. So in other words, sometimes you can learn more from the combination of signatures than you can by looking at those signatures individually, and also pulled inspiration from modern smart home technology. Again, it required us to bring together a highly multidisciplinary team of experts in areas such as NDA systems, in distributed sensing, computer science, mathematics. And I'll say here, we focused for this work on safeguards as a target application for this project. But I think the concepts could also apply in areas like nuclear safety or security, or in operational efficiency. I don't track those research areas myself, but I'd certainly be interested at the end if any of you know of similar research going on in those areas. Love to hear about it. So this project kicked off in 2017 with funding from LANL's LDRD program. So LDRD stands for Laboratory Directed Research and Development. These are basically internal funds that the labs use to kickstart sort of grassroots, high risk, high reward types of projects. All right, next slide. So I mentioned at the beginning of my talk that Los Alamos has a number of unique nuclear and radiological facilities. So for this project, we were able to leverage one of those facilities as a test bed for our study. We combined, access to, these unique facilities with the sizable safeguards domain expertise, as well as some really extraordinary data science and computing capabilities at the labs to pull together what I think is a really interesting and exciting project. So the initial focus of our work was on building the experimental infrastructure for this study. The first year tasks, which is the scope of what I'll discuss here, included the design of a sensor network for recognizing targeted activities, design of the associated data management architecture. We performed scoping measurements using the sensors we had available and did some preliminary data analysis. All right, next slide. Okay, so we had 3 different data streams. The first was continuous monitoring from a helium-3 based neutron detector, which we installed in the laboratory space of the building where the nuclear material is handled. This used standard IAEA hardware and software. We also had nuclear material inventory records. So for this, we had access to the database that logs transactions associated with nuclear material movements between material balance areas within the building and across the lab. We also built and installed a network of 8 inexpensive sensor nodes assembled with COTS or commercial off-the-shelf components. These were meant to be a proxy for surveillance data. So this photo on the right shows what each sensor node looked like. So each was built on a Raspberry Pi computer and had sensors for the decibel level, light, vibration, temperature, and humidity. Okay, next slide. In the 1 year we had for this preliminary study, it took us, most of that time to do the design, build, test, install, get approvals for that surveillance, proxy sensor. So for our preliminary data analysis, we looked at 15 weeks of concurrent neutron data and nuclear material inventory records. So the initial focus was on identifying informative features and correlations that might be useful in building predictive models. And then we tested a number of classification algorithms to identify what we identified as 3 different classes of targeted activities that happen within the building. Okay, next slide. So in order to build basic classification models, the first thing we did was extract features from that data. So for the neutron data, we considered basic descriptive features, things like the mean and the standard deviation over 1 day. And we also did, pulled out some more advanced features. We then used dimensionality reduction techniques to visualize the relationships in the feature space to illustrate how useful features are in separating out the 3 classes. So this plot on the right shows reasonably good distinction between the different activities. Okay, next slide. Once the feature space was built, we performed proof of concept testing on a number of classification models. So in machine learning, classification techniques are used to learn a function that maps input parameters, so in our case, neutron and nuclear material inventory data, onto known outputs, which were the activities that were happening that we knew what they were, so that as new data is collected, we can hopefully accurately predict the state of operations in the building. So on the right, you see confusion matrices that show the prediction probability for each predicted versus true label pair. So they are used essentially to visualize the performance of your model. So basically, the darker the squares on the diagonal from upper left to lower right means your model is performing better. So like I said, a lot of the work that it went into this first year was just building the infrastructure, pulling together the team, understanding how we organize the data. But these preliminary results provided enough confidence that accurate models for activity characterization under realistic operational conditions could be developed. Okay, next slide. All right, so I just wanted to say a few words about the kind of work that I've done in the policy world. Next slide. So as I mentioned, just actually last week, I completed a 2-year detail from Los Alamos to the Bureau of International Security and Nonproliferation at the State Department. So my work was focused on formulating US foreign policy as it relates to the IAEA and developing and implementing diplomatic initiatives in pursuit of US nonproliferation objectives. So I'll say it's a little bit untraditional for a nuclear engineer to do this, but I absolutely loved my time working at the State Department. It gave me a much broader understanding of international security challenges. Technical experts are somewhat rare in those roles. So as my role as a technical advisor, I was able to help translate complex technical issues into policy relevant insights. The State Department also maintains diplomatic posts around the world to support its relations with other countries and international organizations. The US mission to the international organizations in Vienna, called UNVI, represents the United States within a number of international organizations in Vienna, including the IAEA. So as part of my role, I also had the opportunity to work closely with the mission staff there. All right, next slide. I just wanted to leave you with a few parting thoughts before I wrap up. There are a wide variety of career opportunities in nuclear nonproliferation and international safeguards. Nuclear engineering expertise is highly valued in the field. The work is interesting and rewarding. If you're interested in learning more, you can get involved with professional societies like INMM or the Institute of Nuclear Materials Management. And internships and postdocs are a great path to careers at the national labs. That's certainly how I got my start, and how I think a lot of people get in. So with that, I think we can maybe go to Q&A.